Hello and welcome back to High Performance Computing with C. In today's video, the first of Section 3, we're going to learn a little bit about how the CPU is designed and how this will change the way we ought to design our own code. In this section, we're going to take a look at modern CPU design and layout and how this design affects our code's performance, how to stay out of the way of this sophisticated CPU design, and the compiler optimizations that are available to us, as well as how to design our code to take advantage of the modern design of CPUs. And finally, how to use vector instructions to quickly and easily automatically speed up our code using a few simpler compiler optimizations. We're going to begin today by taking a look at how the CPU works. And in particular, we're going to be looking at what makes a modern CPU faster than older CPUs, above and beyond just the bump in terms of clock speed. We're going to see the extra features that modern CPUs have added above and beyond that available in older CPUs, and why it's important to understand this when we're trying to design high-performance code. A modern CPU contains a lot more pieces than sort of a 1980s, 1990s single-core, simple designed CPU that you might learn about in your undergraduate courses. Nowadays, modern CPUs include many cores, sometimes nearly 100 cores on a single die, as well as large amounts of cache, as well as additional control and I/O features. In each individual core, beyond the die itself, there's actually a lot of additional features as well. So if we zoom into a single core, even 10 years ago, one individual core is going to have its area, the sort of layout of the core in terms of how many transistors are focused on one feature versus the next, split roughly into three pieces. About a third of the core is going to be spent on execution. That is, algebra, arithmetic units for doing integer and floating point arithmetic. Another third or so of the core is going to be spent on memory cache. That memory cache is very important because we have multiple layers of memory cache going from the L1 cache, which is the fastest cache, all the way up to L3, and then finally the system memory, getting slower and slower at each point. So the various levels of cache, the multi-layered cache architecture, allows us to smoothly transition between very, very fast memory that's kept very close to the ALU and the floating point units, all the way out to the system memory, which can take sometimes on the order of hundreds of clock cycles to actually access. The final third of the core is spent on decoding, branch prediction, and out-of-order scheduling. In other words, it's spent on trying to optimize your code by predicting the way in which your code will behave. So this extra bits of code are essentially a way of allowing your code to run in an optimized way without having you do very, very fine-grained micro-optimization. It's a way of actually having the CPU work as a second programmer for you in a lot of ways. One of the key reasons that CPUs have grown, not just in terms of clock speed, but also in terms of the features, in terms of all of these additional branch prediction features, as well as these multiple layers of cache, really comes down to timings. The L1 cache, the fastest cache, can be accessed in less than a nanosecond. The next level up from that is almost 10 times slower. And then moving out to main memory is 100 times slower, 200 times in fact. So being able to access things from closer cache levels to the actual CPU can greatly improve the performance of your code. On top of that, branching, essentially going from one piece of code to another based on a conditional, what you might have with an if or an else or a case statement, can be very, very slow, in fact. so predicted by the CPU. So a branch mispredict can actually take 5 nanoseconds, which can be sometimes on the order of about 100 clock cycles or so. On top of that, moving beyond the memory, if we're actually trying to access data from disk or move data from one location over a network or not, we're talking about many, many, many orders of magnitude in terms of how much slower our code might perform. So modern CPU design does a lot for you. In a lot of ways, it automatically takes these things into account. So designing for the modern CPU is less about trying to take advantage of little tweaks about the way in which the CPU is designed, and more about writing your code in a way that it doesn't interfere with things like caching and branch prediction. In other words, it's about getting out of the way of the CPU rather than trying to outthink the CPU. Final thing that's very important in modern CPU design is pipelining. This is the sort of traditional 5-step RISC pipeline where you have a fetch, decode, execute, memory read, and write step, where each of these 5 separate components of your CPU can operate simultaneously as long as they're working on separate instructions. Nowadays, we've moved to a much larger pipeline, about 14 instructions with the latest Intel and AMD processors. It was actually a lot larger in the past. The Pentium 4 era had a 30-step pipeline, but we've realized that a slightly smaller pipeline can actually be a little bit faster. And so on top of the prediction and caching behavior, making sure that this pipeline stays full is the really final step in writing code that the CPU and the compiler convert into a truly optimal version of your algorithm.